We have so many building blocks in agentic system. We have prompt, we have the control flow, we have different tool use, or we may have memory. With some agentic system will even use RAG. And all those things, if we only focus on prompt, all those things will keep fixed and cannot be learned. In this paper, we are trying to argue an approach that we can learn more things and actually all the things in agentic system.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I'm your host, Sam Charrington. Today, I'm joined by Shengran Hu. Shengran is a PhD student at the University of British Columbia. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Shengran, welcome to the podcast.
Hello, Sam. Thank you very much for having me in the podcast.
I'm excited to dig into our conversation. We are going to be talking about your recent paper, Automated Design of Agentic Systems. The work is related to work that we talked about on the podcast with Jeff Clune. That interview was episode 602, almost 100 episodes ago, back in December of 2022. Before we dig in, though, I'd love to have you share a little bit about your background and how you came to study in the field.
Yeah. So I think my research motivation, a lot of them is actually come from the theory about evolution. I'm very curious about the evolution in our biology, in different creatures, and also how those complexity emerge from a very mechanical, purposeless algorithm like Darwinian evolution in our nature. So during my undergrad, I was doing a bit of research in evolutionary computation, a optimization approach that gets some biology inspired from the natural evolution process. And then that led me to read Jeff's work and many of his work really impressed me. So then, and very fortunately, I'm now working with Professor Jeff Clune in University of British Columbia.
That's awesome. So tell us a little bit about the origin of this effort. How did you start down the path of attempting to automate the design of agentic systems?
Yeah. I think first of all, we are really curious at that. Why agent is so popular and why agent is so powerful in many different applications. We're very curious about the design pattern that emerge from this agent and what kind of things it's different from a agentic system design to a single query to LLM, or we call foundation models. And I think all the thinking is actually starting from an analogy between how human complete a task and how foundation model will complete the task. For example, if we query a foundation model, a single query, a single Q&A, ask it a question, say how to solve P equals NP, and then we only allowed it to reply it in a single turn, no extra iteration, no extra reflection or searching online. We feel that this no matter how advanced our foundation model will be, this will be really, really hard. And that's not only true for our models, that's also very true for humans. If you ask me, what's your opinion on P equals to NP? If I'm not allowed to think about it, check about it, search around it, my quality of response will be quite low. And not even the very hard question like P equals NP, like just some very simple question. Is today a very good day for traveling to, say, Vancouver, the city I live in? Well, if I directly reply you, then I would just say, oh, it's a generally nice place. But if you give me more time to think about it, I may start planning. Say, okay, to answer this question, I need to think about what aspects should I talk about when we're talking about is it a good traveling place. We will say, well, how about the weather today? How about the schedule? Can I spare some schedule to travel with you? How about booking some new restaurant? We can get some good food. So with all those planning, and then we need to use some external tools to check for more information, and then we can actually do this task very well. So from that analogy, we believe that agentic system could be more powerful than a single query of the foundation models.
It's a good analogy, and I think at its core is this idea that most of our interaction with the world, at least the more higher level interactions with the world, require some degree of thinking as opposed to kind of a one shot action. But maybe a counterpoint is that, well, and you're also saying that approach is more emblematic of like an agentic approach as opposed to a single query response from an LLM. But a potential counterpoint is all the work that's gone into chain of thought, which is through prompting, asking LLMs to do that same kind of thinking and planning before producing the ultimate response. How does that fit into your analogy?
Yeah, I think the trend of stop prompting, it's actually uh, a bit of agentic. If we can rate the so-called agenticness level, like we just directly ask the question. No, we don't have any requirement. No think step by step. That could be defined as 0. And then if we ask it to do more plan, it's essentially to give it more chance in its response to writing down its own thought, its own planning, and it's kind of automatically conditioned on its previous planning and then solve the task. So it's starting to getting more and more agentics with that chain of thought technique. And then if you involve more techniques like self-refinement or using different tools or and maybe have a memory mechanism, and also maybe you have iterative interaction with the environment, the system is getting more and more agentic.
Yeah, I've got to remind myself to start all of these conversations with how do you define an agent, because it is a spectrum and there are several different definitions. Is there a kind of a threshold for you, or what really captures the essence of agenticness when you think about it?
Yeah, I think I don't have an explicit threshold. I think it's for every different task, we might find a sweet spot in this wide spectrum.
Mm-hmm.
But I feel like we are noticing that there are many emerging or evolving building blocks in this spectrum. We have many very cool stuff getting developed from the community, and also people are investing many different ways to combining them into new system and then applying them to new application. And we feel that is very interesting.
To what degree do you think about collaborative systems of different types of agents or agents with different specialties? How does that figure into what you're looking to do?
Yeah, I think that's a very cool question we will recently think about. I actually have another analogy here. People have actually recently have a very high expectation on the foundation models. That what
Mm-hmm.
we are expecting them to not make many mistakes, to have very good reasoning skill or planning skill. Actually, um, the currently state we have for foundation model, if we put it back to like 5 years ago, 10 years ago, people may already call it AGI. But now we seems like have more expectation for what AGI looks like. But when I think about it, when we think about how human solve tasks or how human collaborate with each other as a organization to solve the task, sometimes we expect the whole organization or the whole the whole structure or whole architecture become stable or robust. But we will not expect every single human in it will never make any mistake, right? Because everyone will make mistakes. I am making mistakes every day. So the important thing is we have this kind of organization. We have this something called workflow or SOP, standard operating procedures. And actually, one very cool example is just the checklist you have given me before the podcast. You you require me to check different things to make sure I have this device, make sure I'm in a good location so that we can make less mistake. So I think that kind of thing is quite important in our agentic system, um, um, because it's very hard to expect our foundation model will never make any mistake. But if we have this kind of SOP or workflow, that foundation model can correct each other, so that we can more likely to have a more robust system.
Your argument there is essentially that even as LLMs get better and their propensity to make mistakes decreases, there's still a place for these multi-agent collaborative systems because the robustness of the system as a whole increases through the collaboration, whether that's checking each other's work or providing guidelines or orchestration of some sort.
Yeah, exactly. But we actually are so during the writing of this paper, we are designing on many decisions on the terminology. And we are very careful about the terminology of multi-agent. We are still not very sure that what kind of system we should call it multi-agent, or what kind of system we should call it single agent. What's the boundary of one agent? Because when we think about it, one agent inside is still not also a single LM query. It inside one agent, they still, if we have some definable boundary, they still have multiple module inside of it. They have reflection, they have planning, they have maybe their memory. So the boundary could be the rule definition, like we define some set of modules, say, oh, okay, you are under one rule, so that's the boundary of an agent. Or so we use different LLMs for different agents, because we know that the diverse perspective from different people, I believe, it's a source of why a system can be robust. Because I can make mistake, everyone can make mistake, but if we are from very diverse perspective, then it's unlikely that we all make mistake at the same time, at the same moment. But we are now experiencing a time that we are using mostly very similar models, or even exactly the same model in our whole system. I'm using GPT-4 series for all the development of my paper. So that's a bit of not very robust if you think about it. If we find a way that can hack in the GPT-4, or we can find a way of successfully inject the prompt to let it do something that is not so aligned, that might be not very good for AI scientist, for AI safety perspective. But overall, I think it's very interesting of this idea of multi-agent, but we kind of need to think more about it on what's the definition and how does it different from our definition on the agents concept.
It may end up being another spectrum.
Yeah.
So a core idea behind the ADAS paper is this idea of AI generating algorithms. Can you give us a brief review of that idea and research direction and how it leads us to the ADAS work?
Yeah, I mean, I think the AI generating algorithm. So this paper is published by Jeff during I think it's 2019, and I think the origin of this approach or this direction is from the observation that in the machine learning community we have a recurring theme that we are replacing the handcrafted design of our AI system with a more efficient learned design or solution. For example, a very, very early example is in computer vision. What we do is we handcrafted some representation or some feature.
Feature detectors and all that.
Yes. And then we realized that we can actually do end-to-end learning. With the rise of convolutional neural networks, we found that if we do all the thing end-to-end, we don't need to design any features for specific tasks. We just define a very powerful architecture to learn them all. And more recent example is actually we can put more data and compute resources in learning more components in AI system. For example, in AI generating algorithm, we will say there are three main parts. One is the learning of architecture of the AI model. One is the learning algorithm of the AI system. And then to generate many learning environment or learning data for our AI system. And some recent example is like recently people trying to actually meta learn the training function or the loss function for the RLHF LM alignment. And people find that the learned loss function is actually better in some tasks, better than the hand designed, the state of the art, say DPO loss function. And this kind of advancement in AIGA is very, very inspiring in us to our thinking in agentic system direction. Because when we think about it, there are so many building blocks it's inventing by the community at the moment in the agentic system. And then people are combining all different kind of building blocks in a new way to create new agentic system for all different kind of application. But the question is, how long does it take for us to kind of discover all possible or all useful building blocks? How many more should we discover or design? And even though even if we discover most of the useful ones, how many effort we need to take from human to actually combine them for every single use case in area of our application. So inspired from that consideration, we believe that the next step could be the automated design of the agentic system to let it learn from the design itself, and then we can meta learn the agentic system design, where we put in more compute and more data and try to learn more component in this AI system.
Talk a little bit about what it even means to design an agentic system. In other words, for the purposes of your research, how did you define the elements of a design that you're attempting to automatically optimize?
Yeah, I think we in this paper we try to describe this newly forming research area, automated design of agentic system ADAS, and we believe actually it has three key components. The first key component is exactly what you described, is the search space. What is the space we are designing our agent system in? So there was some previous work we can consider as some attempts to ADAS. Say we are optimizing the prompts for the LM, when it's trying to doing some tasks. But we will realize that the prompt design is actually a quite small part in the whole agentic system design, because we have so many building blocks in our agentic system. We have prompt, we have the control flow, how different LM calls or foundation model calls interact with each other. We have different tool use, or we may have memory, we may have some agentic system will even use RAG. And all those things, if we only focus on prompt, all those things will keep fixed and cannot be learned. So in this paper, we are trying to argue an approach that we can learn more things and actually all the things in agentic system through a search space in code space, in programming language, because we are representing the agent in a piece of code, and the code space is actually Turing complete. So actually, any possible building blocks and the way of combining them can be represented in this code space. So this is actually a key point in our paper, and that's the first component we believe that is very important in ADAS. And
That sounds
the second,
hopelessly open-ended.
yes, and that's very 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 exciting, we believe. And the second key point we try to argue in this ADAS work is in the ADAS research direction is the search algorithm. How can we explore such a large search space if we define it in a very very flexible way? Say in a code implementation, there are endless possible implementation can happen in the code. So people are exploring all different kind of ways to doing that in the history of AIGA, or even in the history of some early attempts to ADAS. But we believe that if we are going to search in the code space, then a very good option is actually have a something called meta agent to program or invent new agent in code. Because our foundation model, they are very good at coding. So we can actually take a use of this prior to enjoy its existing expertise of the knowledge of coding, and also the knowledge about the foundation model and the agentic system itself. Because it already know a lot about coding and the agentic system, so it can actually propose very novel design or very effective design in code in a very short amount of iteration. So we believe that this kind of approach is very interesting because it can have quite good sample efficiency, and it itself is a very interesting self-referential method, because the meta agent that trying to program and search for new agent, it itself is also an agent that can be improved through ADAS. So this is quite interesting future work direction we are looking at. And also our final key component in ADAS work, we believe, is called the evaluation function. How can we evaluate our generated solutions? Are they good? Are they bad? In what sense are they good? How can we improve them? So so a very very simple way to do that is just test the performance of it, and get a scalar performance reward. Say that's the standard way we are doing currently in this paper. We have a target task, say MMLU or mass or GSM-AK, and we test our generated agent on it, and then we collect the accuracy or F1 score, any performance matrix. But looking ahead, we will feel like there are a lot of possible work actually can be happening here, and lots of interesting possibilities. For example, in real world deployment of agentic system, we will not only focus on the performance. Actually, we will consider many different aspects. Say the cost of the agentic system, how many API calls involved. Say the latency. Even though you have many API, if they can be parallel, then the latency is could be better. And in some case, the latency is very important. And the robustness or safetyness, like we can test our generated agentic system on some benchmark of safety, or we can test how it performs against some prompt injecting attack. So and then I think it's very interesting that we can have some kind of, say, multi-objective optimization algorithm. That's something I have been working on during my undergrad. It's like an algorithm that not only optimizes for one single objective, but multiple objectives for the same time. And then what you get is not only one, the optimal solution. It's actually something we call Pareto from, a trade-off from between different objectives. Say in some application or some scenario, you want the system become cheap, or become less have less latency, but you kind of say, okay, I can sacrifice a little bit of performance here, and then you can choose from the front of the agentic system that have a faster inference speed. Or in some case, you may want, okay, this place, the performance is really important, so I want to take more time, more money in it, and you can choose from the other extreme. So I think there are many different future work direction we can investigate in ADAS.
I commented earlier that the search space being any Turing complete program seems hopelessly open ended and very difficult to tackle. But it does strike me that in some ways one approach could be to constrain your search space to known building blocks, and then have your search algorithm do simple iterations over the known design components, right? Another approach, though, is to have a very open-ended search space, but then implement constraints in your search algorithm, like the components that you're expecting to build these agents out of, or just the approach that you search. And I'm wondering if you can explore like that trade-off. At first blush, it sounds like, oh, you're tackling this wide open search space. But if you then just are shifting the constraints over to your search algorithm, like what's the difference? And why even have them as separate components?
Yeah, I think that's very cool thinking. And actually, we think quite a lot about that, because in theory, we can allow our meta agent or our search algorithm to construct any possible agent in programming language. Theoretically, that's completely possible, but in practice, that may be very inefficient, because we have
I think
so
you'd
many,
have to give it some direction.
yes, because we have so many basic functions in our agentic system building, like how to query a OpenAI API, say, or cloud API, how to formatting the prompt, how to manage the information flow between different modules. So in this work, actually, we are doing a very simple investigation that we give it a very simple framework that is less than like 100 lines, and then it did help it to define the function of query the foundation models or LMs, and formatting the prompt automatically. So then it can only define something we call a forward function, and then to describe the behavior of agentic system using those existing function calls. But also it can develop its own function call, as we observe from the experiment. it will define its little bit, say, many of these meta agents generated the generated agent, they like to have a ensembling technique. So they have implemented a little majority voting function in their design of agent. And we found that is quite interesting way to explore our code search space. And also we believe that this is actually a benefit of our search space to define in code, because we can use the existing human effort building blocks that they are available there. Say we have a lot of existing LM or agent framework, and human already build a lot of cool stuff in there, all different kind of tools, maybe a implementation of reg system, how to automatically format the prompt, and 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 if we define our agent in code, then that means that we can just simply take those um, existing efforts from the human and then put them in the search space as the existing building blocks, and then our algorithm can actually start using them, and that will be a lot more sample efficient than build everything from scratch. Although building everything from scratch is very fun for research purpose.
One of the diagrams you show is one of the agents that was discovered in applying the framework to Arc. And it displays a fair degree of complexity. Like, there's a bunch of chain of thought, there's several different types of experts that presumably this agent, the ADAS system discovered and built into this agent, et cetera, et cetera. There's like more complexity. And so now I'm thinking about, I guess I'm trying to wrap my head around like where the turtles stop, like, the turtles all the way down thing. Like, is the ADAS system itself similarly complex? Is it actually very simple? Like, does it just have access to like, search and an LLM, and it can build all of this complexity from very simple building blocks? Like, does the complexity need to co-evolve? Like, how does that all work?
Yeah. So as we just described, I think a very very cool future direction is to have, say, agent all the way down, that we
Right.
have a meta learning of the meta agent itself, that we can have meta agent.
Mm-hmm.
But in this work, we are trying to demonstrate our simple idea first. Our meta agent currently in our implementation is a hand designed algorithm, and it's quite simple agent where we just prompted um, some related information, like how the given framework looks like, what's your task, and what's the previous discovered agent, and then we ask it to build new agents, and then we allow a few rounds of on the reflection to make it help to improving its own result. And basically that's it. We are applying a quite simple design of meta agent.
So it's a relatively simple framework that is heavily relying on the built-in intelligence in some external LLM that, given a rough code framework and an objective, can spit out some code that kind of fills in the blanks and essentially, is the design for a new agent.
Yeah, and actually for the results of, we are actually getting some results that we are very excited about, because we actually observe, as you said, the complexity evolve from a very simple set of building blocks. So what we provided as a seed is like the existing manual design and very classic design patterns like chain of thought or reflection, and those the seed we give them. It's no, there are not many very complicated things in the seed. But then as you mentioned, in our one of our experiment is in Arc. Arc challenge is a very popular reasoning challenge these days, and it tries to access the general intelligence of AI systems. And our funnel agent or the best performing agent we discovered in Arc through this ADAS algorithm is actually quite complicated. It has a lot of, as you said, sealed chain of thoughts, and it have a very complicated feedback system that it have multiple experts that are expert in different aspects like readability or simplicity of the answer. And then they also have something called a human-like reviewer. The problem is actually say, okay, you are now emulating a human giving a feedback to this solution. And we are very curious how those complex mechanism evolved. Is it come out from nowhere? The LM just program it? So when we look at the history of the discovery, and we are very surprised actually, this kind of feedback mechanism is a combination of 3 different stepping stones that occurs previously in the history. So that is something we are very excited about. So because we are doing a research direction called open-endedness, we try to learn in an open-ended way and discover a lot of building blocks, and then we can combining those building blocks into a more powerful solution. And then what we exactly see here is a very good full example of how this kind of open-ended algorithm can discover all different kind of stepping stones. Because when these stepping stones appear, they are not the best performing architecture. They themselves alone is not performing so good. And then, but our algorithm automatically realized that although this currently does not perform so good, but this has some potential. If we combine them together, combine them previous discovery or stepping stone together, we could get some more powerful agent. And it tries so, and it actually get quite good results. So this is something we are very surprised about.
This design process is an iterative process, and with each successive iteration, the search agent has access to the kind of the prior history of discovered agents. Do you find that complexity in this environment, in this setting, is like monotonically increasing, or does it exhibit, for example, like the ability to identify abstractions and like simplify? And maybe an intermediate question is like, how many iterations is it even stable? Like, does letting it go for more iterations necessarily produce better results, or does it, is there a tipping point after which it gets unstable and like it really only works for 3 or 4 iterations?
Yeah, I think that's a very cool question according to how we design actually the search algorithm. There are many different ways we can design our search algorithm. One point is that so there is a classic problem called exploration exploitation trade-off in optimization. So we in one hand we want to explore more to um, explore around the search space, finding new design. Maybe that's not something related to previous discovery, but we want to try some novel things. But on the other hand, we want to get some more promising solution from the experience we learned from the previous discovery. So it's, as you said, things might get a little bit more complicated with combining those previous discovered stepping stones. And for now, what we are doing is actually quite simple. We just, in a very fuzzy way, we ask it in the prompt, you can decide whether you want to explore some new idea, or you want to learn from the archive to combine some existing stepping stone. And we discovered that in our experiments that it will kind of alternatively do exploration or exploitation in a quite fuzzy way. And sometimes you will want to explore some new ideas. Sometimes you want to build the uh, better solution from the previous discovery. But we will anticipate that one could investigate more about the design of this search algorithm. Do we want to have some prompt design for exploration, or have some prompt design for exploitation, and how can we trade off between these things? And this is quite interesting. And for the search generation, it's actually surprisingly very sample efficient. For our ARC challenge, we only do 25 iteration of design. So in total, you only design like 25 different agents, but it already outperformed the state-of-the-art handcrafted agent by a substantial margin. And we think this is this efficiency thanks to the prior that foundation model have about foundation model themselves and agents and coding, so that they don't need to during the search to learn those prior from scratch. They already have those prior, and so that they can from the generation one, it already starting to generate some interesting agent.
And does each iteration result in an agent that performs better than previous iterations necessarily, or
not necessarily? Yeah.
Okay.
We'll believe we'll find that, because in our prompt, actually, we encourage it to do more exploration. So sometimes you will try to explore some new idea, and that's unlikely to have an immediate improvement on performance. But as we just described, all the discovery become the stepping stone for future new invention.
Yeah, it's interesting that you mentioned that in your prompt, you're suggesting to it that it can combine previous solutions or not, and that it's not the combination that you described prior wasn't like some emerging property. It just did it on its own. It's part of the way you're prompting the system to use the history that you give it.
Exactly. And actually, from the open-endedness research from our lab, we found it's a very straightforward and effective way to encourage the open-ended learning of a foundation model system. Is that in the prompt, we explicitly ask it, is this solution you generated novel? Is it interesting? And then let it reason about why this is novel and interesting. And then through this way, we can encourage them to discover some novel, interesting, and more exploratory solutions.
So all that said, did you observe it discovering novel approaches, not novel solutions? We just talked about that, but novel approaches. Like, were there any kind of emergent behaviors or observations or things that it did that weren't explicit in its prompting?
Yeah, we actually discover quite a lot of interesting design pattern emerging from our discovered agent. Say one design pattern we found is actually very useful in ARC challenge, is that because for ARC challenge, the question is you are given some input output example of some grids, and then you need to find the patterns or find the transformation rules for those input output grids, and then I give you a new grid, and you need to answer me what the output grid looks like. So a common practice in this domain is actually not directly let the AI system answer what output grid looks like. It's actually let them to generate the code that implements the transformation rule learned from that few short example, like 2 examples. And then we can actually test the generated code on this given examples and then apply them to the test question. And one design pattern emerging from the design of the ADAS algorithm is that they will try to generate a diverse set of a lot of program or a lot of transformation rules they predict, and they write different kind of Python program to try to predict what kind of transformation rule is actually going on here, and then they can evaluate on the given example input output to see the see how good is the generated Python program, because a good solution, a correct solution, should pass the existing example, and then it can pass the test example. So an emerging pattern is that in many different way, they will generate a lot of candidate solution, and then they store it in the memory, and then they rank it through the success of the input output patterns we get as the examples, and then we can do a huge example among those good solutions. And once those patterns emerge from the search, it becomes the dominant patterns in our archive, and every following architecture or agentic system try to follow that pattern. And we believe there's something quite interesting observation from our experiments.
That is very interesting. I think I was also trying to get at like higher level, meta behaviors or things that maybe a way to frame this question better is like, you started off talking about your research interest in kind of the evolution of cognition and that kind of thing. Like, if you were to map this current project to those kind of objectives and learning about how reasoning and cognition has evolved, like what might you do different, or like how might you instrument your meta agents, or what do you think there is to learn about the way that this system is working, if anything?
Yeah, I think one very interesting thinking we are having is actually through this ADAS approach. It could be, well, one way is it could be a way that we can better understand our current foundation model through its automated design, because that's also happening in many AI generating algorithms practice, say in neural architecture search. By observing different kind of neural architecture that emerge from the search, we can actually learn more about some insights from the convolutional neural networks. And also the same here, because when we are applying the algorithm to different foundation models, because different foundation models, they have different things they are good at or they are not performing so well at, and then we might have different agentic system search from those foundation models that are using to evaluate those agentic systems. One example we discover is quite interesting here is when we search. So all of our search for saving the cost, we use GPT 3.5. It's a relatively weaker model but faster. And during the search of that, we discover it, as what I described, it have a very complex feedback mechanism, and that's the optimal solution. Optimal solution if found during the search for GPT 3.5 model. But we zero shot transfer that model to some more advanced model, say GPT-4 or Cloud 3.5. And we realized that this no longer be the optimal system design. The optimal system design becomes something that generate more candidate solution and focus more on the refinement steps and the example step. So that might hint that GPT 3.5 may have a weaker ability in evaluate themselves solution, so that they need a complex feedback loop to to enhance that capability. And we will believe that if one try to understand more about the behavior of foundation model, the ADAS could be an interesting direction to explore. Another thing, as you said, my personal motivation of research, I'm very interested in how complexity involved in a system. For example, in our society or many of our human organization, we have very complex pattern. I'm very curious, can this kind of pattern also evolve from a bottom-up approach? And I believe actually ADAS is a cool way to investigate this kind of observation, because we will find a lot of relationship between the agent work and the the, the architecture of human organization or the human society. Say there is a work called MetaGPT. They try to um, emulate a software engineering company. They have different character or rules of agent acting in the software development team. They have like team leader, they have software developer, they have tester, they have designer, and then all those so-called agents collaborate with each other, communicate with each other. They try to design a software. Or we can see some artworks, I think it's from 2023, they try to use ChatGPT to simulate a human village, like the interaction between different NPCs. And all those things actually, they are behaving in an agentic system. They have a design of agentic system that how each module or each component interact with each other. And if in ADAS, we can allow the evolution or emergence of more complex design or interaction between different components, maybe we can understand more on how human organization or how human society evolve those complicated organization or architecture.
Yeah, I'm finding as we discuss this and as I think about it, the idea of the flow of complexity or the evolution of complexity in the system to be a really interesting idea to explore. And also um, how that complexity might be like abstracted by the system in some way. And if that helps it deal with more complexity, like, maybe, um, you know, is there a way to prompt it to kind of consolidate what it's learned about past systems by creating some DSL for agents and then starting to think in the context of like these predefined components that it creates, or these, this DSL that it creates, or, how the system might manage the complexity beyond just keeping lines of code in memory. But then maybe, on the other hand, maybe that's the advantage that the LLM has that we don't, is that it can keep a bunch of code in memory and not have to create those abstractions. It'd be interesting to see how that plays out.
Yeah, exactly. We believe that there are I think we are keep describing a lot of exciting direction
Yeah.
that we can open up through this early investigation to the ADAS.
How close do you see this being to practical application? How far down these future paths do you need to go in order for this to have some utility?
Yeah, I think, well, for us, we are in this paper, we are more like academic orientated work. We are trying to demonstrate this scientific argument more. So all our algorithm design or our framework, I tend to keep it as simple as possible. But recently, to my surprise, and we are very excited to see many developers in agent community actually giving us some good feedback about they try to use our algorithm in their application. And one of the developer on Twitter, they said code, they get very, very interesting results after applying ADAS to their system. And one another developer post that they say, "Code, after 1 hour of adaptation, we can simply apply the ADAS approach to their system." And we believe that that's very, very interesting to see more people trying out this approach in the practice, more practical application. And we are very, very excited to see how they goes.
Do you know if that means that they use an ADAS or an ADAS-like approach to design an agent, and then they kind of extract that agent and apply it to their task? Or are they, is the implication more like an ongoing optimization using ADAS as part of their solution?
I'm not exactly sure what our people's doing, but what we anticipate is actually for one possible use case is when there is a new use case, when there is a new application, we can just use ADAS to automatically design the agentic system to apply to those specific applications. We just need to give it some basic building block and see how it goes. If this ADAS algorithm can build some workable solutions to effectively solve some of tasks. And then one another application we think is quite interesting is that if we have a working solution like a agentic system that already can work on some tasks, and ADAS can become something similar to continual learning, because during the deployment of the agentic system, we will get a lot of feedback from the practice. Say, I think a very cool analogy I'm thinking this morning is that I'm reading the checklist you sent me about the podcast. And I actually wonder, what's the first version of the checklist? It's like you must experience something in each bullet point so that you will write those bullet points.
Right.
So I think that kind of thing is very important in agentic systems, or even in any human organization. That's the way we evolve.
And that's exactly where the question was coming from. Like there's a clear place and design time, like just, here's my problem, spit out an agent that will, solve this, or an agentic system, let's say, that will address this issue. But then also, so much of machine learning AI is like closing the loop with the data and continuously improving the system. And it seems like there would be a role for that as well, but also some risk, like, you have stability risk, like you're continuously introducing new code, like you have to vet that code. Just seems like there are really interesting challenges in there, but also opportunities.
I think so.
Very good. Well, Shengran, thanks so much for taking the time to share a bit about your research and all things ADAS. Super interesting work. Thanks so much.
Thank you so much for having me, Sam.
Thank you.